When engineers evaluate the health of a complex networked system, they typically rely on active frame state summaries. They pull data exclusively from the nodes that are currently online, responding, or visible. This generates the metrics you see on standard monitoring dashboards: the average load over available servers, the average error rate across non-failed components, or the mean anomaly score among participating agents. But there is a mathematical blind spot built into this method. A network's average anomaly can register as quiet and stable, even when the system can no longer route the traffic it was built to carry. That discrepancy occurs because the global average of a network tells you almost nothing about its demand relative functional capacity, its actual ability to connect a specific source to a specific destination. Take two identical networks. State A sustains distributed damage. State B suffers a structural failure, cutting it in half. Both networks output the exact same anomaly score of 0.15, yet their actual function is entirely different. State A routes traffic. State B is severed. This is the central finding of a 2026 paper by independent researcher Joshua Duran. Through rigorous testing of synthetic network models, Duran demonstrates that active frame anomaly is structurally insufficient to infer demand relative functional capacity. Relying on these active averages creates an illusion of health. It allows catastrophic structural failures to hide in plain sight on a monitoring dashboard. To understand why this happens, we have to look at how active frame anomaly is calculated. The equation divides the sum of all local anomalies by the active set, the total number of nodes currently participating in the network. That denominator is the source of the bias. The metric only performs its arithmetic on nodes that are still alive to report their status. When a highly anomalous node completely fails, it drops offline. Because it is no longer participating, it vanishes entirely from the active denominator. By removing damaged components, the global average instantly drops. The network reads as safe, completely ignoring the structural hole left behind. The required countermetric to this illusion is demand pair effective conductance. Effective conductance doesn't care about the average state of the nodes. It measures true capacity by testing whether intact, functioning paths still exist between specific source and sink endpoints. Duran uses a capped functional score for this, limiting the maximum value to a baseline of 1. This strict cap ensures that any temporary super baseline conductance isn't mistakenly counted as system recovery. Network function is entirely relative to demand paths. When a monitoring system continually shrinks its denominator to drop failed nodes, it actively obscures local failures from the global view. Exposing this bias required testing the networks under highly controlled conditions, and early iterations of this research actually contained a mathematical trap. The initial model used an additive anomaly update to simulate damage, but the additive model had a structural flaw. Its uniform anomaly mode possessed a multiplier greater than 1. This created supercritical dynamics. Instead of anomaly mass naturally spreading from node to node, the mathematical environment artificially amplified the total damage across the entire network. This chart displays the result of that earlier equation. The massive blue bar on the left represents 1,648 frames of dramatic false recovery, damaged networks actively feigning total health. But Duran corrected the methodology. He replaced the additive update with a mass-conserving diffusion model. Under diffusion-corrected dynamics, propagation redistributes the anomaly smoothly through the network, instead of artificially multiplying it. This graph details the outputs after the correction. The dramatic false recovery frames completely vanish. The count drops to 0 for both the Watt-Strogatz and random geometric graph diffusion models. A pre-registered local removal test confirmed it. The sensational false recovery phenomenon was not a true feature of the networks. It was an artifact of unstable math. Stripping away that artifact allows the research to isolate the core result. Even under stable, corrected dynamics, active anomaly fails as a sufficient statistic for network health. That result emerges clearly in the primary testbed for the corrected diffusion model, the Watt-Strogatz runs. Within this data, we find the twin phenomenon. A twin occurs when two completely independent measurement frames display the exact same non-zero active anomaly score. But despite having identically matched anomaly readings, these twins operate at sharply divergent functional capacities. This plot maps the Watt-Strogatz twin sets. The x-axis represents the matched anomaly, and the y-axis is functional capacity. Tracing any vertical line shows one anomaly reading corresponding to two totally different levels of routing function. This is not an isolated glitch. The dataset identified 228 distinct low anomaly twins. Their median matched anomaly sits solidly at 0.152, but the median gap in their functional capacity is 0.724. One network is highly capable, and the other is severely impaired, yet the dashboard reads them as identical. Smaller-scale random geometric graph runs produce similar twin sets, serving as a narrow, independent corroboration of the Watts-Strogatz findings. With a median functional gap over 0.7, these twins demonstrate that the active anomaly reading is functionally blind to a network's actual capacity. A rigorous audit has to ask the obvious question: are these twins just a mathematical glitch caused by anomaly scores bottoming out at 0? If the values are effectively 0, of course they'll match. This histogram tracks the exact distribution of the twin pairs to check for that floor artifact. The dashed line marks the 0 floor boundary. As you can see, the twins do not clump at 0. The matched pairs are distributed well within the non-zero interior of the dataset. In fact, 99.3% of the twins have matched anomaly values above the 0.05 threshold. The gap is real, and it survives skeptical testing. But checking for errors also means examining network geometry, specifically the physical distance between source and sink demand pairs. The data clearly shows that a network's functional spread is sensitive to where you place the demand pairs relative to the initial damage. This chart compares the physical layout of these routes, revealing a major baseline route construction confound. Pairs located far from seed damage start with a massive structural advantage. Their median shortest path length is just 1, while near-seed paths are 6 times longer. Because of this built-in structural difference, you cannot make broad claims about spatial placement without first running matched route controls. Demand geometry clearly influences exactly how a network fails, but the fundamental insufficiency of the active frame metric remains independent of spatial confounds. The locked result of Duran's research is straightforward. Active anomaly is not a certificate of network recovery. Two identical frames can exhibit vastly different capacities to carry traffic, and this happens even when active network mass is perfectly intact and mathematical dynamics are strictly subcritical. The danger in an operational environment is total misdirection. If you are monitoring a massive enterprise system, a quiet dashboard can simply mean the network dropped the failing components and stopped doing the math on them. Modern engineering protocols cannot afford to rely on active frame averages as their primary proof of health. Systems that depend on routing paths must utilize rigorous functional tests. They need demand-aware proxies, or measurement frames that actively preserve and track inactive, broken structures. A low anomaly metric does not equal recovery. It merely indicates that the anomaly